Okay, good afternoon, everyone. Once again, thank you so much for joining our second webinar. And today we are privileged to have Dr. Udochukwu Bola Akuru, who is a senior lecturer at the Tshwane University of Technology in South Africa. His core research interest is in the design of electric machines for electric power and renewable energy. And so we're really excited to hear his perspectives on the exciting topic of from wheels to words, powering Africa with retired electric vehicle motors. So without saying much, I will hand over to Dr. Akuru.
Okay, thank you very much, Prof, for the introduction. I want to say good afternoon, or perhaps maybe good morning or good evening from wherever you are joining the webinar this afternoon. I am based in South Africa, specifically in Pretoria. So that is why I am referring to it as afternoon. Yeah, so with this webinar, so what we are going to try to do here, we are just going to try to unpack what we basically want to do with the CEPREC project. So in terms of the CEPREC project, I just want to say that it is a multi-million pounds grant that was awarded by the UKRI. And under the grant, we have basically 9 work packages. So my focus in that work package is, on the different work packages is specifically on work package 1, which looks at the second life exploitation of EV components. For myself, specifically electrical machines. I have my colleague, Prof. Lai Alatishe at Warwick University, who is looking at the power electronics aspects. So it's a big project. It involves a couple of countries, as we can see, 9 institutions from up to 6 countries between the UK and in Africa. And yeah, so basically that is what I will try to do with this webinar, just to give some perspective and also to give some scope. So nothing really elaborate in terms of the technical work we have done so far, but in terms of exploring the possibilities as we look at converting EV end-of-life components to electricity. So like I've been introduced, my name is Udochukwu Bola Akuru. I am the South Africa as well as the TUT CEPREC lead for the project. Okay, very quickly, I will be looking at my talk under the following subtopics. I will start with an introduction to give some context. Thereafter, I will present the technical potentials of end-of-life electric vehicle motors, after which I will look at the electric vehicle motor repurposing strategies that are documented, and hopefully we can deploy some of these in the studies we plan to do. Then, of course, the main motivation for us is how can we repurpose these vehicles, the EV vehicle components in a microgrid setting in sub-Saharan Africa. So I will look at some of the concepts and maybe topics of interest that we have to explore in order to be able to achieve the goal, after which I will give some conclusion. Okay, on that introduction, I'll be talking on the following. So let me quickly jump on the first part of it, which is energy access in sub-Saharan Africa. So I think what we all will agree, especially those of us who stay in this side of the world, is that electricity, it's a big challenge here for us. So there is a lack of it. And of course, it results in a lot of ripple effects in terms of access to healthcare, education, productivity, jobs, and the likes. So basically, it hinders our progress in achieving and delivering on the SDGs. As a matter of fact, the World Bank reports that 600 people currently lack access to electricity in sub-Saharan Africa. And for myself, who is based in South Africa, out of that number, almost more than half of them are based within our sub-region. That is, if you look at it within the Eastern and the Southern African region, specifically 365 million. So it's a big challenge. But of course, in the midst of this challenge, we have seen that distributed renewable energy systems, the so-called DRE systems, is the game changer for us to be able to close this gap. And as a matter of fact, we need to scale up our efforts. And that is basically what we hope to achieve using the microgrid concept. In terms of the global outlook on EVs, which we want to use in the project. So what is there is that the market is growing. And if we really preach sustainability, then it must converge in terms of secularity. So at the end of the day, we really need to indeed protect the future while we sort of meet the current demands. So of course, EVs are being touted as renewable. So it sort of decarbonizes the sector, the economy, and creates opportunities. And that is where we all want to head to. So, but of course, with the growing number of adoption of electric vehicles, in a very short while, we may be faced with a new type of challenge in terms of the end-of-life products that result from them. So basically, that is what I want to explore in terms of my work package under the project. So for Africa, what are the potentials? So in Africa, the potentials, I mean, sort of cuts across a lot of aspects, but specifically in terms of greenhouse gas emission reduction, if we sort of decarbonize and apply circularity with the growing resources that will amount from adoption of electric vehicle infrastructure. And of course, we can also take advantage of some of the resources that we are endowed with in the continent. So basically, we are looking towards the future. We are really, forthright in our thinking in how to really approach sustainable development in terms of energy production and use. Okay, so basically, like I've said, in a few years, we will end up with this challenge of having electronic waste. And the question that we will all be asking ourselves is, how do we manage the electronic waste that result from the electric vehicle industry in terms of the different components? Specifically for myself, it is in terms of the electric vehicle motors. Okay, so on that basis, I want to delve into the motors, which is the second part of my talk, looking at the technical potentials of the end of life of the EV motors. I'll start by giving a short story in this part. A short history on electric motors generally, and the configurations of electric vehicles, the components in electric vehicles, the different electric vehicle motor types, PM materials, as well as the characteristics of electric vehicle motors. So here is a short history. there is a famous museum in the United States, specifically in Washington, called the CEPREC Museum. So when you go to that museum, there's a big picture on the wall as displayed on your screen. So this is the Hall of Fame of people who have contributed in the development of the electromagnetic energy conversion. Specifically, we look at people like Michael Faraday, who first of all proposed the electromagnetic conversion theory. And of course, the next person online is William Sturgeon. So William Sturgeon was the first person who actually developed a motor in terms of a DC motor. That was in 1932. I beg your pardon, 1832. Then, of course, we have Nikola Tesla, who came up much later with the induction motor, as well as Galileo Ferrari. So these were two independent researchers who were working independently, but they came up with the same product at the end of the day. But of course, Galileo Ferrari is being touted as the one who first developed the theory of multi-phase, rotating magnetic field, while Nikola Tesla was the actual person who developed the first multi-phase AC induction motor. And I was in Torino last year for a conference, and basically on your screen what you see is the prototype of the motor developed by Galileo Ferrari in 1885. So his concept was based on the single-phase induction motor concept, but of course Nikola Tesla is being credited mostly with the patenting of induction motor, because he developed the multi-phase induction motor, which, as we all know, has disrupted the industry. And of course, generally, electrical machines led to the second industrial revolution. So there are other names like Edison and the likes who all had some contributions in the field. Okay, so that's basically the short history I want to give. Thereafter, we have motors like synchronous machines and so many other motor technologies today. Okay, so having said that, let's look at the configurations of EV, the electric vehicle, basically, to understand where the motor is and how important it is in the architecture. So we'll look first at the, in terms of how the electric vehicle is excited. So, so if it is if it is excited with the internal combustion engine, as well as electric power, we call it hybrid electric vehicle. So that is the first configuration there highlighted. And the next one is your plug-in hybrid electric vehicle. So of course we say plug-in because here you have opportunity to charge the vehicle. So there's an onboard charger within the vehicle, unlike in the first case where you only mount the batteries. Then of course we also have the battery electric vehicles. So these are the fully electric vehicles. So there is no hybrid supply. It depends only on electricity. And of course, right at the top there is your internal combustion engine vehicle topology. So all these topologies have their series, parallel series, and parallel powertrain configuration in terms of how they are configured with each other, the hybrid system. So specifically within the configuration, we have the components of the electric vehicle. So the components of the electric vehicle are highlighted as you can see on the screen. So I start with the charging grid. So for an electric vehicle, there must be a source for supply. So that is your charging grid, followed by your charging port. In this case, where there is a plug-in. So we have the charging port where we plug in the charger. And of course, you have the battery charger. Every one of us have a mobile phone. I want to guess so. So your charger of your mobile phone is taking the same way as the charger of the electric vehicle. So that is how we power the batteries. And of course, we do so using, we do so based on the battery pack. that is seated in the vehicle. And of course, there's a battery management system that monitors and also controls how you charge your battery and the life of your battery and all these kind of things. Then there is the power converter, which when you have your battery, basically it gives you output power in DC formats. But most of the electric vehicles are AC motors. So that is why we need a power converter to convert, DC to AC. After which we also have the power inverter. So the converter sort of modulates the DC voltage, from one level to the other. And then there is a conversion from DC to AC using the inverter. And lastly, here is our guy, the electric motor. And for me and my team, that will be the focus, our focus in the CEPREC project. Okay, I just need to mention that in this whole system, the process, the power flow is from electrical to mechanical, basically. So the concept of electric vehicle is you feed in electrical power as an input, and you, get out mechanical power as an output. And of course, the electric vehicle motor is a major component for this to happen. And needless to say that having it in an electric vehicle, it's usually operating, under a very harsh as well as mobile condition in terms of stop, starting, acceleration, deceleration, variable loads. So it has to be rugged in order to meet the demand. So electric vehicle motors are quite rugged. Okay, having said that, let's go generally to options for electric vehicle motors. So there are many options, as you can see on your screen. Broadly speaking, we have them as brushed and brushless motors. So brushed motors are motors that uses your commutators and slip rings to convert, to keep the supply to the exciter in a particular form, maybe DC or AC. In this case, for a DC, it will be DC. For a one-field synchronous motor, it will be AC. So you have your brushed as well as your brushless motor topologies, broadly speaking. And I've listed them as shown. You have under your brushed motors, your DC motor, your electrical excited synchronous motor, your electrical excited induction motor. And then for your brushless, you have your squirrel cage induction motor, permanent magnets motors, synchronous reluctance motors, switch reluctance motors, and other emerging types of motors that I actually work on, mostly your so-called flux modulating machines, like your one-field flux switching machine. Okay, so there are pros and cons as we look at the motors. So for DC motors, basically the challenge we usually have with DC motors is the efficiency of the motor. And so basically for your brushed motors, so efficiency, reliability is always the problem with these motors. But for your brushless motors, that problem is managed, but they are faced with their own problems. For example, your squirrel cage induction motor, it has, it can run at a very high speed, but of course the efficiency is also a problem because it uses what we call slip rings, and it has caged rings. So basically that sort of takes some power from it when it needs to operate because it works on the principle of induction. Then of course the power density is also not so good. Because for these motors, one of the desires is to make the power density high enough so that it can be compact within the vehicle. So therefore, the permanent magnet motors have become dominant because these motors provide better efficiency as well as high torque density. But they have their challenge. The main challenge is usually the cost of these permanent magnet motors. Then, of course, there are other topologies like this synchronous reluctance as well as the switch reluctance motors, which sort of solve the problem of the permanent magnet motor in terms of costs, because you have robust rotors with them. So with these motors, you have a robust rotor. There is no permanent magnet or field excitation. But the challenges with these types of motor is their torque performance. There's usually high torque ripple for the switch reluctance and poor power factor for the synchronous reluctance. So it's always a trade-off for the manufacturer in deciding what kind of motor they use in an EV vehicle. But you will see as we move on, the motor that is of dominant use. So here we see a chart showing motors being adopted in different types of, by different type of manufacturers for different type of EV vehicles, your fully electric vehicle, as well as your plug-in hybrid vehicles. So it is clear from industry perspective that the permanent magnet motors are the preferred motors. And why is that? Okay, the reason is simple. So on your screen, basically, you see the, we call it the BH curve, but maybe not necessarily one in this case, because it's the axis, horizontal axis is showing the trend of development over the years of these magnets. But normally the BH curve also looks similar. But of course, as you look over the years, there has been some improvement with the energy that can be extracted from these magnets. And that is why the permanent magnet is the preferred one, because currently we have, a lot of energy that we can get using the permanent magnet as an exciter for your motor compared to any other excitation topology. So, but like I've said earlier, the problem of these high energy magnets is their cost. Okay, let's look at the EV motor characteristics. So the important thing with EV motors is that they operate based on the constant power speed range curve. So basically what this curve simply shows us is the behavior of the motor during start and also when it is cruising. So during start, if you look at the blue curve, that is the power building up. So it builds up to rated at the rated speed. But we expect, because for your conventional ICE motor, that is your internal combustion engine, when you start, you want to accelerate immediately. You don't want to stay there and people start pushing. So that is why the torque must be at rated when you are starting it. But the problem is from the curve, you will notice using the charts, you can see the motor efficiency usually is designed to operate at the rated point. So most times between the cruising point as well as the starting point, the efficiency may not be very good. So, but of course, there is always a trade-off that manufacturers want between the starting as well as cruising. So the cruising is when we get to the constant power region, and there we can weaken the flux in the machine and push the speed further, but without changing the power. So this is a very important curve, and it tells us the behavior, the characteristics of an EV motor. And what we can see from the industry is that, so if you look at this curve, basically what you see is most of the manufacturers, for example, you can see your Nissan, your Toyota Prius, which was a benchmark in the industry, your Ford, and the others, they basically use permanent magnets currently. Some started with induction machines, for example, Tesla, but currently maybe a hybrid of them, because it depends on how they configure the machine. Sometimes they use forward wheel as well as rear wheel drive. So most times there are such trade-off, so that maybe during start, they put an induction motor in the front wheel so that it can accelerate. It can gain traction. Then during cruising, the front motor is relaxed and the rear motor is activated for cruising. That is like a permanent magnet motor. I think that is one of the latest technology that Tesla is using. But from this, I just want to paint out some picture. So we compared 4 different motors. This is a study done by my PhD student, by the way. So we compare 4 different different motors. And we can see that the permanent magnet motor, gives you the best efficiency as well as the best torque density. But of course, like we said, cost is always the issue for this motor. So there's always a trade-off between, what the manufacturer wants and how much they are willing to go for it. So this is maybe more insights on different type of motors. So here's a comparative study of different type of motors using the benchmark motor, which is the third generation hybrid electric vehicle motor of Toyota. So that is the start point. If you look at your screen, the start point is actually indicated. Yeah, so the start point here is your Toyota Prius. So what we can say from the motors, the comparison here is normally this is where electrical machine designers want to operate: high torque density, high power density, and as well as high efficiency. But you can't usually get both working very well for you. But at least if you look closely, you would see your Toyota Prius, giving a benchmark because it's a permanent magnet motor. But of course, the emerging motors, like I said, your synchronous reluctance motors assisted with ferrite to improve on the power factor, they seem to be catching up as well. So that is why you have them maybe getting high efficiency. But of course, you can see the torque density is not so good. So it's always a trade-off. I just put this chart here. I'm not going to tell you this is the best motor or not, but normally this is a trade-off for the manufacturer to decide. And as you can see in the previous slide, different manufacturers have different needs and demands. Okay, let's go to the EV motor characteristics and how it will apply to what we want to do with the microgrid power generation. So, like we said, the motor operates in a very harsh environment, start, stop, acceleration, and all. So it's dynamic. And it's not stationary. But for a power system, if we will repurpose, like we are trying to do, the motor from an electric vehicle, one of the game changer is that the environment will not be as harsh as it was for an EV motor. So we can begin to ask ourselves some questions. Will the motor work for the purpose we want it? For example, high torque density, high efficiency. Well, I think it will work because the industry perspective is towards high torque, permanent magnet machines, which shows high torque density and high efficiency. And in a couple of years from now, when the industry saturates, we'll be getting a lot of e-waste from that part. The other thing is, will the motor, after its end of life as an electric vehicle motor, will it yield a good reliability? I think so, from the arguments we've given that we are moving from a mobile application to a stationary application. Then the other thing is, will it be adaptable for a generator? Because most times, yes, basic electrical machines will say every electrical machine, every electrical motor is an electrical generator. Well, on paper, that is very correct. But in reality, it may not really be the case. We're talking of motors, and generators and motors apply to specific industry, having specific demands and requirements. So basically what we may need to do here is adaptation. But of course, already from the application of electric vehicle motors, we know that we can apply regenerative braking, where we can get back energy fed into your batteries using the motor. So we are trying to also explore that. Then lastly, the important question will be, will it be low cost and low speed? Because we are trying to bring it to our situation within Africa, where we believe this will be very, for low cost, it will be a very important factor. I think so. For the simple reason that your rear earth permanent magnets are already very expensive. And at the end of life of a motor serving an electric vehicle, the permanent magnet's life would not have ended. taking the magnet off, recycling it is a process altogether. We are going to come to that very soon. So I believe that just repurposing that magnet, that motor, for the purpose of generating power could be a low-cost endeavor. And of course, the low-speed argument is in terms of, your EV operates at high speed, even at rated. So, but most of the applications, especially for the kind of applications we're looking at, we don't want to introduce cost index further. So we could decide to use gearboxes, but that may bring some new demands, even beyond costs, in terms of reliability and all these kind of things. So can we also reconfigure? And I think that is the most difficult question we will be facing in the project. Okay, let's go quickly to the repurposing strategies that are there, that I have sort of explored and hopefully we can apply in our study. So just a small background. In this case now, the power flow has changed. So we are now going from mechanical to electrical. That is power generation. So, and the options are many in terms of the source. So take note, your motor sits right here. So just to point out to you, so your motor sits right here. Your machine or your motor sits here. But we need something to power the motor. We need a mechanical turbine to do that. And the options are limitless. But of course, for the kind of motor in terms of power rating and all this kind of thing, we may not, explore every option, and also the location where we hope to site the microgrid. So these are questions in the work, but for now we are thinking wind and we are thinking hydro. Okay, having said that, so the two motor of, prominence in the industry are the permanent magnet and the squirrel cage induction motor, but I will focus more on the permanent magnet. So this is just an idea of the different components in the motors. And most times what researchers are doing, they are trying to recycle these components to, reuse the motor, but that is not going to be our objective here. It's an option. So like you can see from the screen now, so what you have on the screen is basically the different approach to circularity of EV motors. So we can reuse them by simply repairing them or repurposing them. So this is where we want to sit. Or we could remanufacture, we could upgrade, that is a different term altogether, or we could recycle. So recycle means we have to basically dismantle the motor, disassemble it, and sort of redistribute the parts through a recycling process. We will not want to go through that route. And we may not also want to go through these other two routes. So this is where we want to operate, whereby we can quickly reconfigure the motor, repair where necessary, and reuse the motor immediately. But there is a caveat there. So when we do that, the performance of the motor definitely will not be the same as it was originally designed for. So what will be the trade-off? These are questions for us to answer as we move on. Okay, so basically a brief literature review from my side reviews. This is not my study, by the way, but of course, based on the literature, it shows that the interest, mostly even from manufacturers, to recycle is clear from the graph, or remanufacture, little on reusing. So I think it's a lot of opportunity for us, especially from what we are thinking. I guess maybe the reason why it is not a lot of reuse, the EV industry is still emerging. It has not saturated, so to say. Maybe in the next few years, 5 or so, the industry saturates and maybe people can begin to think more about reusing the motor because of the waste, electronic waste that will result as a result of it. Okay, I will go next to the next thing, which is the testing and the validation. So yeah, these are just concepts based on, insight that I've gathered from the literature. We are looking at end of use versus end of life. They may mean sometimes the same, but not really so. So of course, we are trying to exploit the second life. But if we cannot exploit the second life, then maybe we can say the life is ended, end of life. So we are basically looking at the end of use, maybe for one purpose to another purpose. So one of the things that are necessary for us to do so is to inspect and diagnose the motor. And that will depend on what is the condition of the physical life, what is the life cycle, that is the second life of that motor. So, I mean, we don't just want to make it work and within the next few months it breaks down. So these are things we will be doing in the project. What will be the level like? So will there be a cost benefit? Will it be better for me to go to the market and buy a new motor? Or I can use this motor as I'm trying to do. So these are some of the concepts we'll be looking as we test and validate. And yeah, so we go through a lot of processes like failure analytics, motor application in terms of same industry. For example, here we are talking of renewable energy or reliability in terms of moving from mobile application to stationary, performance in terms of what is left of the motor, the second life, the efficiency, and more importantly, the cost. So we'll be doing some life cycle cost analysis as well as levelized costs of energy analysis in our study. And there are different things that cause motor failures. I don't want to go into them, but basically it balances within the electrical, mechanical, as well as the environmental and maintenance factors. So the opportunity here is for us to explore the development of a standardized assessment approach for evaluating and monitoring the condition of EV motors so that we can come to a point where we could say, okay, this motor has reached its end of life. We can, I mean, apply it in a different perspective. From the literature, we are not seeing this, and this is an opportunity for us. And of course, the electrical, mechanical, thermal diagnostics of existing EV motors are things we want to do, and it costs across the different tests, as we have shown: resistance, continuity, insulation, static and dynamic, mechanical in terms of visual inspection, vibration, ultrasound, as well as thermal in terms of the thermal capacity, load of the motor to survive its second life. And lastly, I would also want to talk about adapting these motors to generators. What are the opportunities? So we'll be looking at the end of life characterization for stationary power generation, the cross-sector industry moving from EV to wind. Of course, it's still within the same, so to say, industry, renewable energy. The size of the motor will constrain the application. So your typical size of electric vehicle motor is between 100 to 200 kilowatts. And of course, when there's been degradation after first life, we want to know what percentage will be left and how would that apply in a microgrid setting. In terms of how do we put it in wind and small, I mean, in hydro, will it be small wind turbines? Will it be roof-mounted wind turbines and stuff like that? Adaptation, of course, from high speed to low speed power generation. Very important thing that we have to, look at in the study. And there are limits. So that can only be done within the windings, the poles, and the frequency of the motor, and maybe drive interface. So we'll look at the options and decide which is best to go. And also, of course, the thermal picture, as well as the mechanical picture of these motors, predicting the new lifespan, as well as integrating these motors to the microgrid hybrid system. So we are looking at a system where we could have other sources. What will be the interaction, and what will be the system level analysis? There are people working in this project who are actually looking at that, and we want to see how to integrate our proposed solution with what they are doing. And we can also maybe look at other application use, like for the emerging renewable energy grid. We know it loses inertia. Is there a potential for us to still, well, I think that would be stretching it too far for a microgrid application. Okay, I quickly round up. So in summary, what I have basically said here is that to accelerate the decentralization of electricity microgrids across the sub-Saharan African region, we have basically seen some insights on the second life exploitation of end-of-life electric vehicle motors. And some key considerations have been drawn, but these are not the limits of it. For example, inspection and diagnostics, motor reconfiguration, thermal management, load adaptation, as well as integration to the renewable energy grid. And of course, locally for me here in South Africa, and I guess for most of my colleagues working in other countries, is how what we do in alliance with what our nation's the national priorities of our nation. Here in South Africa, the national priority is for just energy transition. Exploring all the options of energy resources. And I think, and I believe this is a good direction we are heading to. And of course, the opportunity to create jobs and opportunities for the technology to be localized. Okay, I would end here. Thank you for your attention. This is some of the references and my contacts if you want to engage more. Otherwise, thanks for joining. Over to you, Prof.
Thank you very much, Bola. Thanks so much. That's very interesting. I guess now what we'll do is just to open the floor to questions. Okay, so let me see. First, we have Sarah. I will allow your mic. Sarah, you can unmute yourself now.
Right. You can hear me now?
Yes.
Okay, right. Thank you very much for the very important presentation. I'm not a motor expert, so therefore my questions might look a bit stupid, but let's see. Now, in the EV application, the motor is essentially operating on a variable speed and as a motor. And then when you come to, we'll have to get it to operate as a generator. So one of the first things that came to my mind is the machine might have been optimized to operate best or optimally in the variable speed operation. And how will it behave as a generator at constant speed? And the constant speed, perhaps we might be able to choose it where it gives you optimum efficiency, perhaps. But then, of course, the voltage that needs to be generated is going to be a consideration. I think the EV motors are perhaps rated around about 230 volts and 400 volts, something like that AC. So the mini grids or the electric system also will have to operate at that particular voltage. So those are my observations rather than a question. So there I rest my case.
Thank you, Prof. Since it's some observation, let me pause. Maybe we can take some questions. I will answer if I need to. It's quite interesting argument, but I think we have some answers already.
Okay, thank you. Let's go to Rita. You can unmute yourself.
Okay, thank you, Prof. Muiwa, and thank you, Prof. Bola, for the presentation. It's really been insightful. So my major question is about what is that major key failure that motors face in EVs that could affect the reuse application in renewable energy, especially for the permanent magnet synchronous motors?
Thank you for your question. So can I go on now?
Yes, please.
Okay. So yeah, so the key failure. So I was just lost with time, so I was trying to accelerate. So for permanent magnet, the key failures usually is thermal. The main problem is usually thermal problems in permanent magnet motors, based on the magnetization of the motors. And basically, that is why we will be doing some failure analytics. It still remains to be seen how we will access these motors, or in what form we will access these motors. Will we get them as, end of road e-waste, where we just go and pick them from the dump site and try to use them? Or will there be some type of return by customers to manufacturers? And we have some understanding with the manufacturers that, okay, I think we can't continue to put this motor on the road. And at this point, we need to repurpose or recycle or whatever. So if that is the case, then the motor is still operating, but maybe it's at a point it has reached its first lifespan. And we won't take it at face value. I mean, every engineering design has its risk analysis. So that is why we will be doing some failure analytics. So we'll be looking at the thermal aspects of the motor. We'll be looking at the electrical aspects of the motor. So what is the real performance of the motor? And how long can we still operate this motor now when we repurpose it as a generator? So these are some of the things we'll be looking at. But the main failure is usually thermal, which is based on the magnetization of the permanent magnets. Yeah, maybe to answer that question. Then the other comment by Prof. Yeah, it's a very good question, but of course, that is what we will try to do. Let's not forget this project is not being done in isolation. My colleague, Prof. Lai, is looking at the drives, the power electronic side, the wind drivetrain, proposed wind drivetrain, if we want to use wind power, just for saying, involves the power electronic converters, and that solves the problem in terms of the power exchange. For voltage, we can easily convert the voltage from a level to another level, so that shouldn't be a problem. The end users can be able to use the voltage at a safe level or the standard level. Then for the speed, that also solves the problem because wind is going to be intermittent. So the only challenge will be if we are designing the motor for a hydro. Yeah, so maybe that could be an issue. Yeah, because we want to fix the speed and, I mean, supply the power. But of course, who says the hydro cannot also be interfaced with a power converter? It is still something that we can explore especially for a small application. We are not talking of large hydros where we cannot start building very large power converters for such a system. Okay, thank you.
Thank you. So, Botha, Dr. Botha, yes.
Afternoon, Dr. Akuru. I've got 3 quick questions for you. The first is, will you be looking at integrating other components in the EV system, such as the inverter, which obviously is already voltage rated for the system, cooling systems, etc., into the wind turbines or hydro or whatever? The second question is, have you looked at the end-of-life cost evaluation for that motor? What is it worth in terms of the ownership structure on the EV owner side? Is it worthwhile to sell a vehicle that's very end of life and strip it for parts and then repurpose that for wind turbines? And then the third question will be, since you're going to be doing wind turbine, it has to be high speed, which means you have to use a gearbox. They're almost all water-cooled machines. So you're going to have some stability problems regardless of what you do, because you're going to, in your back-to-back converter, you'll have basically no inertia. Would it be beneficial to repurpose the EV batteries in a much lower current draw application to stabilize that inertia side of the equation?
Okay, thanks, Dr. Botha, Stefan. You asked very important questions as an expert in the field yourself. So, yeah, so like I mentioned, the project, maybe I just need to run a bit to the front to spare some details. So the project is a consortium looking at the different, aspects of a microgrid as well as the electric vehicle. So of course, the electric vehicle, I've shown the component is not made up of just the motor. There are power converters, and so our objective here is repurposing as much as possible all the important components. And one of the important components in the electric vehicle is the power electronic converter as well as the battery. So if we will be integrating what our solution with that of other components, the answer is a possible yes, depending on what we find out at the end of the day. What is the best solution? Because everything is based on the research. And please, let's take note, we are still at the beginning of the project and we are asking the same questions you are asking. So I think that would be my response to the first one. The second one is the cost evaluation. Initially, it was something I was advised against, but doing some background research, I noticed it's a very important argument. It will keep coming up and we just have to clarify it, which hypothetically, I believe it will make economic sense to repurpose than to buy a new generator, considering the end of life of that motor. We want to believe it will be a waste and not a secondary product that we have to buy, or even if we have to buy it to be subsidized, so to say. Okay, so I think we will be doing those kind of analysis. So if we bring in a gearbox to the system, because the motor is high speed, what will be the trade-off in cost if we repurpose the motor, maybe work on the windings and maybe reconfigure the windings and change the speed to a low speed? What will be the trade-off in terms of the output power? When we interface it with the power electronic converter, what will be the cost trade-off? When we directly connect it to the grid, what will be a cost trade-off? As much as possible, we will be making some of these analysis, but it's something we have not done yet. Then, of course, maybe the high-speed gearbox you already mentioned, in terms of the battery coming in to support the grid, that there are colleagues working on it. You can see on the screen, the second work package focuses on that. Myself and my colleague in Warwick will be looking at the power electronics and the electrical machines, and you can see some other solutions, thermal energy and the others, modeling of the grid as well in work package 4. And also there is the social science aspect, lest I forget, in this project. Thank you.
Thank you very much. So we'll go to penultimate person, Chinedu Titus.
Yes, good afternoon, Prof. Can you hear me?
Yes, we can hear you.
Yes, we can hear you.
Good. Thank you for the wonderful presentation. I've been hoping to hear this presentation. And this presentation, I was kind of lost because I was looking for the relationship or that of a common hybrid electric vehicle to relate with other electric vehicle. Because when I heard of energy from waste to wax, I was more of thinking about the energy from the regenerating braking to make the electric vehicle a standalone, because cost index, which you said you did not go into that, would have been what could determine the performance of the electric vehicle that we are discussing based on based on performance and reliability and costs. Because since you didn't go into that, and I was also confused about the terms recycle, remanufacture, reused, all those terminology. Are you referring to maintenance or repairs or something like that in the electric machine parts? Thank you.
Okay, no, thanks a lot. I get your point. So the first part of your question, which you are trying to clarify, so we are not using the regenerative power. That's not the aim in this work. It's not our focus. We are not using the regenerative power in the motor because we have simply transitioned from an EV and to a microgrid system. That is the objective. So a mobile system to a stationary system. So I think that's the simple answer. We are not working with the motors, but we have to look at the motors because that is where, so that's why it took some time to give some background on the motor, because that is where we are getting the products from, but we are not working on the motor. Okay, so quickly, I just want to go to the, sorry, I was rushing the different aspects of, reuse, remanufacturing, and recycling. So basically for reuse, what we are talking about there, so I think I'm almost there. Yeah, so for reuse, what we are talking about here is we are looking at the motor. So it has reached its end of use for a particular application. For example, I guess you will be more comfortable that an electrical machine fails as a generator than as a motor that you are driving in. So an electric vehicle motor is a very how do I put it now? So taking it from the application that it serves as a motor, the chances of failure should be as low as possible. But for a microgrid system where we have a stationary machine, take note the microgrid is going to be isolated from where people are. That's the first thing. There will be some protection around the microgrid. That's the next thing. So even if there is a failure within the microgrid, at least the direct harm to people will be minimized. So that's the idea behind the the fact that we are trying to exploit the second life of the motor and using it for a generator. So for reuse, we are expecting that there is still some life in the motor and we can adapt the motor basically to some other things. So that's basically what we are doing. But when you talk of remanufacture, so for remanufacture, what we are looking basically at is we are taking the motor from the beginning and we are trying to remanufacture it from the beginning, which it may not be a sustainable thing to do within the project that we are actually considering. It's not something that this particular project will be looking at in terms of remanufacturing. Then also there is the issue of recycle. So recycle is the case where the motor has completely died. So we take the parts. So in recycling, basically we are converting the materials that we would have otherwise considered as waste now to reapply them in different products. Now you may talk of household equipment. So basically we are disassembling the motor, completely crushing it and trying to recover some valuable materials like the different parts of the motor, the steel, the copper where necessary, and using them for secondary purpose. So, but reuse, sometimes we may not even open the motor. And I think that's the sweet spot we want to work in this project. We just want to maybe look at reconfiguring the windings, or maybe even if we open the motor, we are not taking off the permanent magnets. We are trying to see how to work on the windings, maybe to convert the speed, or maybe interface it, in the system level to the power electronics converter. Okay, I think that is all I would say. Sorry, I tried to scroll towards the chart I had, but I think it took me all the way. Yeah, this one. Yeah. Okay, thank you.
It's good. It's good. I've understood. Thank you.
Okay. I think, is that all signatures? That's your question.
Yes, Prof. I see some question on the chat. I don't know if I can take. I think it's the same question. I can take it.
Yeah. Yeah,
Okay.
mine is on the chat, so I think no need. You could look at it, but anyway. So my question was mainly looking at European and especially European EV car manufacturers. Their focus is on recycling of most EV parts, right? So I foresee, have you looked at the feasibility of potential, let me call it competition for lack of a better word, because most of these car auto manufacturers will seek to get their parts back to recycle and remanufacture vehicles due to several reasons. I mean, the mining, materials, and all that value chain. I know there's a work package on value chains, but then have you looked at that feasibility? Because you're looking at reusing these motors for energy generation, yet vehicle manufacturers are thinking about circularity where they can harness most of the vehicle parts to
Now your question is clear.
recycle
So
them.
so it's not under my scope of work, but I believe colleagues under the project will actually maybe consider that. It's a big question from my side. Where are we going to get the resource for our proposed solution? Or how can we source it? So I think there's that social science aspect that we engage with the industry, and I mean, maybe the markets, the potential, and product availability, and all these things. But you are very correct. Currently in Europe, they are recycling. Like you said, because of the cost of new materials. But I think maybe what we can also look at is the economics of doing that. So under the scale of preference on costs, will it be better to buy a new material to go through the recycling process? How developed is the recycling process? There is actually a study I stumbled on from the UK that was actually looking at the different industries. And basically, most of the, I think I put the chart there. So most of the industry players, they said they were not recycling the motors. They were just, I mean, they were not. So that's the chart here. This particular study. So they said they are just reusing. I mean, recycling it. They are not reusing it. Why are they doing that? I didn't delve more into it, but I think you are very correct with that. Okay, so very quick, because of time, what happens if one of the repurposed motor generator fails? Say it magnetizes or overheats. Who do we hold accountable? Is there a warranty we can lean on, or we will need to arrange our own insurance or product liability? So basically, the research will cover this. So these are the risk performance analysis. We will look at it in our study. That is why we are predicting the remaining life and the failure capabilities of this motor. So we are not just taking a motor at face value and testing it and saying, okay, it's now, maybe it was 50 kilowatts before, it's now 40, let's say, just for say 40 kilowatts. Okay, where can I apply this motor? No. 40 kilowatts, what is the reliability? How will it depreciate over time? How long can we use it? So we are going to do some prediction, condition monitoring of these motors. So of course, the risk of it failing is not going to be on the side of the user, but on the side of the manufacturer. But our study will be able to predict all this and tell us the chances. I think that's all the question. Have you looked at the cost-benefit analysis of repurposing end-of-life EV motor for energy generation, given that? Okay, I think that's the question I just attended. What are the opportunities for collaboration between academia and entrepreneurship in the adoption of EV motors for wind and hydropower? So this is a very good question. Prof. Muyiwa, should I leave it for you? I mean, I believe when the product is available, we are looking for this kind of collaborations to take it to where it is needed.
Yes, definitely. So collaborations is all what we're about. I guess if you just stay in touch with us, we are working on some things that will be of use to people. But yeah, thank you so much, Bola. Very interesting, and thank you all for attending. We have gone a bit over time, but yeah, we will have to draw the curtains now. Thank you for your engagement. As he said we are the Circular Economy Powered Renewable Energy Center, and our mission is clear, just to see how we can stimulate knowledge in Africa to drive the energy transition using leveraging circular economy principles. So please, if you're not yet engaged with us, you can follow us on LinkedIn, or other social media channels. But we look forward to engaging with you more in the coming months. And then watch out for our next webinar, which will be next month. Thank you and have a good day.
Thank you. Bye-bye.